Hello everyone, it's May 25th. Alright, let's do this today. Largest color value in a directed graph. Here is a directed graph of n colors, n colored nodes, and m edges. The nodes are numbered from 0 to n minus 1. We are given a string colors, where colors I is the lowercase English letter representing the color of the ith node in this graph. You're also given a 2D array. Edges indicates that there is a directed edge from AJ to BJ. A valid path in the graph is a sequence of nodes from x1, x2, all the way to xk, such that there is a directed edge from xi to xi plus 1 for every one of them. The color value of the path is the number of nodes that are colored, the most frequently occurring color along the path. Return the largest color value of any valid path in a given graph. Okay, so in this case, we have these colors. So if we go with a path, a valid path is a sequence of nodes such that there is directed edge. The color value of the path is the number. The color value of the path is the number of nodes that are colored the most frequently. So if we go this path, we have 3, right? But in the largest of any valid path, on -1 if the graph contains a cycle. So there's a -1. So essentially, what we're looking for is we have a graph, right? We have a graph and we can find any path in the graph. And what we want to know is, given a path, what is the count of the most frequent value in this path? Now, of course, the longer the path, the better. So it may be beneficial if we just start from anyone and just keep going, right? Is the graph connected? Didn't really say. We can try. See if the graph is connected by taking away 0, 1. It doesn't matter. Connected or not doesn't matter. But how about we including this? We have a self edge on 1. That should be -1. So any time you find a loop, that is a bad thing. Okay, that's fine. What I'm thinking is, we start from anyone, right? And we can find a counter of colors. A counter of colors. The thing is, like, you start from a node, right? You start from a node and you have multiple, right? You have 2 paths. Let's say you have 3 paths, okay? Now, each path, let's say this one tells you what, like a counter of the colors on each path. They can have many paths. And which one should you return? Right? And what is the maximum? And the thing is, the maximum for this is not necessarily the same as the maximum for this. Right? And this one I can say A is maximum, this can be B is maximum. And when we go here, we have the compare, right? We have the compare. And the thing is, this one can have multiple paths as well. Like, which path does this one choose, right? So let's say this is A, this is B, this is C, this is D. Each path has a different color. And coming here, I can say, yeah, like, let's say this is A. So coming here, A definitely wins out. Let's just say A wins out, right? However, this is, let's say this is B. Alright, A wins out in this, but if I take B, then B, even though it doesn't win out here, but it will win out there. That's the difficult part. Yeah, we start from something. We can just walk. We can get all the paths. That's the same. We can also get all the paths, right? Because there will be a leaf node. And you always respect the leaf node because you get longer path always has a higher likelihood of. So, okay, so instead of thinking about this, let's think about a leaf, right? Each leaf represent one. Then you don't know where the root is. There's no root. You can say I start from 0, okay, so you get whatever value you get. But then you have a different one come in and it connect to 0. Then what? How do I tell immediately? Well, if you come down to 0, right? We start, let's say we have some graph like this, right? This is 0, okay? So we go that, and then what we get is like reaching here. The path reaching here. And it can also be like this. We can have multiple reaching here, right? Yeah, that's why the state needs to save in this node. But how do I save the state in this node? I mean, I have all these nodes. Each one can have multiple paths. And each path, children, right? So this can have multiple, and then each one, but it's the max color for each path. That doesn't work. Because the max color path is not necessarily the one getting picked up. I have to take a holistic view. But it is a directed graph, which means we shall be able to find the root, right? Yes, it's a directed graph, so there definitely exists a root. If there's no root, like what do you mean by there's no root? That there's no starting nodes. Right? There gotta be a starting node. Which means this is what we can do. Initially, we need to find all the roots. And the roots are the nodes that have no integers. Right? If there's no such, that means you have a node that has out degree and in degree. So everyone has in degree. If everyone has in degree, that means that means there is a cycle. If everybody has in degree, so in this case we can check the number of in degrees, right? So 0 is 0, 1 we have 1, 2 have 1, right? 3 has 1, 4 has 1. Yeah, 2, 3, 4, 1. So the only thing that does not have is 0, right? Which can also be checked. Yep. Do you need teeth? Okay, yeah, I'm back. So now we know who the root is, and then we just DFS from the root, go through everything, come to the end of the path, and then check which one is the largest. It sounds good. And it might have multiple roots. So like in this situation, so 0 has an in degree. right? In this situation, this is good, but this is bad. How do we tell? We cannot tell from the integrity because we I mean, technically we can. So the initial search, the whole purpose is to find the root. If there's no root, then yeah, it's bad. But if as long as we have a root, we have to check it, right? So in this case, we check it and then we go through everything. And now we try from 2, but this one visited. 3 is visited, 4 is visited, 1 has not been visited, right? So now I start visiting 1, and we find out we cannot visit 1. Yes, yes. So every time we visit, it has to be, if something has not been visited before, then it's on the top level, then its in degree has to be 0. If not, then that's okay. We have some idea of how this can be done. Let's see if we can code it up. Alright, so idea is 1857. Since the graph is directed, if it does not contain a cycle, there must exist a root who has 0 in degrees. We will use this fact to find all the roots. Then we will perform simple DFS to find the max color count for each path, right? And return the max count. Alright, so the first step is we have to build a graph and we have to do the in degrees. So we'll go first, we'll do this size, okay, and we'll do in degrees, okay, and we'll do graph. That's actually good enough. And then what we're gonna do is for const auto pair edges, okay. So E0 to E1, then in degrees E1 plus and graph E0 dot pushback E1. Okay. So that's that. Okay, that's that. And then we'll say for what else need visited? Okay, so vector of Boolean value visited. Alright, so for int I0, I smaller than ni plus plus, right? If not visited, visited I, right? If I not visited, if in degrees I is equal to 0, okay, then we'll do DFS. DFS, we have I, and pass graph, and pass colors, We need to pass a counter vector int of 26. Right, so these are the three things we need to pass, else return -1. Right, so this is a cycle. A unvisited node, but not a root, must be a cycle. And we'll do everything, and we also need a value which is int res 0. So we'll do res as well. And at the end, we'll return res. Alright. Now the job is void dfs int node std vector of std vector int. It has to be actually it's going to be a constant because we're not making any change to the vector, to the graph itself. So that's a graph. What's next? Graph and std vector of int counter. Okay, counter. And this has to be a reference. The reference goes with reference goes with this, right? And at the end is a reference max count. All right. If node, actually, we will go when we have a node. Oh, and a color. I forgot a color. Color. Const string. Std string colors. Colors. Yeah. All right. Cannot bind temporary. All right, so I cannot do that, but it's fine. We can just define another one. Counter 26. Okay. So we'll do 26 counter. Okie dokie, and now we're good. So we have the current node, right? The current node. Then what do? We will add it to the counter. So we say counter colors node, okay, minus a plus plus. All right. And then I'll say for int child of graph node. See, this is where things might get a little bit tricky. Yeah, they might also have like cycle. It'll cycle back. So like if it visits something that has been visited before, so I need to get visited as well, but I don't see visited is in here. All right, so graph colors here is visited. Vector of bling visited. Okay. Visited node equal to true. Should I visit this node? So I go down, I go backtrack, and go to the other one, and in this one path, right? If I need to return something. No, return boolean. Right, now we just say if visited node, I already visited, return false. Okay. And here is the same. So if not this, right, this is false, return -1. Colors before counter visited. Right, this is a cycle identified. Okay, so here is the same. We say if DFS child graph colors visited counter max count is a false, return false. Otherwise, yeah, otherwise it's fine, right? Otherwise it's fine. So I go through all of them and but hold a second. If I visit a node that has been visited before, yeah. Okay, so I visit all the children and I don't care, but at the end I need to find the max value. I think C++ has find max in vector. I know there should be a function call, right? You're kidding me. Oh, here, max element. Yeah, max element. So I just pick the max element in the counter for the moment. And we can say max count shall equal to max element counter dot begin, counter dot end, and the max count, right? And then I'll return true. Max element is a max element has to be star this thing. Okay, after we've done that, and we have to backtrack. Right, so this is backtracking because we hold a counter, so we have to backtrack. And let's see if this one works. Well, I hope so. All right, let's try it. Nope. I think I got this one wrong. Yeah, I think I got this one wrong. It should be if integer is 0. It should be something like this, right? If it's not visited, then we check. If it's 0, and if it's not oh no, it's right. No, it's right. So we say if it's not visited, and if its in degree is not 0. Okay, how about let's just be a little bit dumb and don't do this check. Just if it's 0, and it's false, right? If it's 0 and if it's false. Okay, let's try. Huh? Yeah, can do that. Okay, so let's restore to the last submitted. And this one is bad because I say this is but it should, okay, that's all right. Let's give it a check. So we have 0 to 1, 0 to 2, 2 to 3, 3 to 4, 3 to 5, 5 to 6, 2 to 7, 6 to 7, 7 to 8, 3 to 8, 5 to 8, 8 to 9, 3 to 9, and 6 to 9. I think what happens is right, I visited. This. Yeah, if you want to backtrack, you have to go full backtrack. Ah! Now this one becomes wrong too. What? This is weird. Hold on. This is very weird. And there are a couple more things that I need to do. For example, if graph node dot size is larger than 0, then I do this. Else, this is then we do this. And now I backtrack. Alright, let's just figure out what the hell happened. I have no idea. I feel like it's right, but it's not. Right? How the hell the first one is also wrong? Alright, let's just take a look. I don't like this, but colors. What? Yeah, we'll have the debug. Just 0, 1, 1, 2, right? 0, 1, 0, 2, 2, 3, 0, 2, 0, 2, 2, 3, and 3, 4. 0, 1, 0, 2, 2, 3, 3, 4. Okay. That's that. And then this shall be longest. No, largest. Colors and edges. Okay, let's put the thing here. Wow, debug every day. Debug every day. Alright, let's see what the hell happened here. Let me give it more space. Okay, well, we have a graph. Yeah, graph looks fine. 1 doesn't have 2, 3, yes. And we also should have something called, oh well, it's not. We have graph, we have color. Color is fine. Visited should be nothing or false. Yeah. Counter should be nothing. And max count nothing. Okay. So now visited color, I think it's A. So yeah, this one plus plus. Visited is true. All right. So size larger than 0. Yes. So child. First child is 1. That's fine. And I'll do that. Okay, so now node is 1. Node has not been visited. 1 is a different color. So color counter, yes. Visited is true. And it's larger than 0. No, because its counter is 0. So I do else, and max shall be 1. Yes, max is 1. Then we're done. And counter, so this one shall go back to 0. Yes. Visited, this shall be false. Good. Return true. Okay, so this one return true, which means we'll keep going on to the next child. Alright, next child is 2. Then we go inside 2. This is no. 2 is a again. So A become 2, yes. Yes. And then yes, that shall be a 3. Yes. So we go 3. 3 is this color, yes. And then it's larger than 0, yes. And I get child is 4. Now we go 4. Okay, so we got 3. There should be 0. Okay, max now becomes 3. That's good. And then I'll reverse the color, so there should be 2. And this shall be false. Okay, going back. Now notice 3. We done. Right, we done. Coming here. I reverse. Yes. Oh, I think I know why. This is all fine. This is all fine. Hold on, actually I don't know. Let's keep going. Now this is 2. I'll reverse this. Yes. Now we go 0. Done. 0 will reverse. Okay, everybody got reversed. Where are we? So we are here, right? So this one return true. And nothing. So I now is what? I is 1. Ah, but 1 has been visited already. Damn. Ooh. But it's fine because it's... Oh, I see. I see. Visited is a pretty darn thing to do. Yeah, because it's backtracking, that's why it's kind of hard. Backtracking makes it a little bit difficult. If we don't do backtracking, then we need... Because I need the value at the end, so we kind of have to backtrack. But then if we backtrack... And we can have... Oh, visited counter. None of them works. How can we do in degrees? If we visit something, the in degree shall reduce. So essentially, if there is a graph, if there is a cycle along the way, right? If there is a cycle along the way, it will be identified, and then we're only going for I equal to 0. Therefore, I equal to 0. But then, how do you know that one of them has not been visited? So what you're saying is there should be 2 separate visited. That's essentially what you're saying. We need 2 of them. Gosh. One is to be used during the traversal to see if there's a cycle, right? That one is not really cycle detection. Okay, so yeah, that's just more space. So we have visited, that's the overall, and we also have vector cycle detection. Detect cycle. In cycle. Okay. And then visited is, this is the global. Right. Global visited state. Is cycle. To be used in each path, each DFS path. It's like a path, right? It's like a path. I was trying to like maybe counter can help us with this, but no, it cannot. So I still need this, right? Visited. If it's this, yeah. And here we can say visited is a cycle. Path in path. Okay. In path. So after visited, we need one more. std vector bool in path. Okay. And in path node equal to true. This do not backtrack. In path backtrack. Do not backtrack visited. It is used. It is for global use. Here we don't check this. We check in path. Okay, now let's try. Sorry, add one more part to this. Now we're good, and we need to do one more check, which is this. Once this is done, we can submit. All right, looks decent. Let's submit. 49 minutes, a little bit longer than how I wanted. I mean, if it works, I'm not sure it will work. It does not work. Why does it not work? 0, 2, 3, 0, 1, 3, 4, 1. What the hell? You should identify 4 is the 1. Did I identify 4 is the 1? What? Wow. Hmm. What? Try again. What is wrong? Huh? Hmm? Oh, nothing has. Wait, hold on. What the hell? That's right. In degrees. Oh. Not visited. In degree is not. Huh? Oh. Okay. So this is a wrong way of. Well, if you're not visited, then. If you see. Oh, okay. Alright. Let's. Okay. Let's do it the other way. So basically, if you're not visited, okay, and your in degrees is 0, then your root, okay, then we'll try this, right? Then we'll try this. If not visited, and you're this, and we try this. And eventually, once we're done with everything, all the nodes should be visited. If there are nodes that have not been visited, and it's also doesn't have in degrees is 0, right? So basically you go through them. If the in degree is not 0, then you don't visit them, which is fine. I mean, okay, you can, we can sort, but yeah, let's not go there. Yeah, so you go through them. If it's not visited, it has to be in degree as 0, right? So you visit all of them, and what I'm worried is in a separate one, right? You have things that's in degrees not 0, you're not visited, you're not 0. Then you will have things that you do not visit, right? So you have some nodes that you basically don't visit, which means there's no root for them for you to visit. Therefore, at the end, you should just check, we should say for int I equal to 0, I smaller than n I plus plus. If there is a visited I, then I should return -1. Right, so some node is not visited, right? Has not been visited. Some node has not been visited after all the roots have been have been visited. That means the unvisited nodes cannot be reached by a root, indicating that it is in a cycle. Being visited. All right. Let's try this. We add another. Jeez. We add another check. That's another ON right here. Now I'm getting worried. Yep. As I had expected. TLE. Alright, so we don't know. Well, let it. I thought it was fine. I seriously thought it was fine. I don't know why. I mean, backtracking. We visit every node only once. How come this gets so slow? I don't understand. And this one doesn't look that bad. It must be something. Like maybe I got myself sucked into a cycle. But I have cycle check. There be it has to be in the current path, right? We're in the current path. That's how you get a cycle. How come this is so hard? I don't understand. Okay, there are a few things maybe that I can do. For example, I don't know if this helps. I don't think it helps. Was it just slow or what the hell is wrong with this one? No, I think it must got stuck in a cycle. How is that even possible? Zero, one. 0, 2, 1, 2. Boom, boom, boom. That's not a cycle, right? This is not a cycle. But you are revisiting, yes, because this has already done whatever it needs to do. I already get it. But then you do this way. You're visiting this again. Ah, that's right. You're visiting it again. Okay, let's get the solution. Oh shit. Let's get the solution from here, and then we will. This is not even. We're gonna do Python here. So we say this is a copy paste. This is a copy and paste. Must solve it again. Must solve it again. Make sure it works. I'll submit it, but have to solve this again. Do this. Go back to C++. Yeah, basically it means we have to have a DP, stuff like that. We can't just redo it every single time. Okay, yeah, we'll think about how this can be done. All right, I'll see you guys tomorrow. Adios.